John left me the dirty work because I really do have to ask everybody who does not have a seat to leave. I apologize. I regret that there's not more space, but we have firm instructions from the Teton County Fire Marshal to honor the room limitation limit, which is 130. That's on the back wall. And at jeopardy of losing our relationship with the Teton County Library, we have to ask everyone to honor that. So apologies. We don't often max out, but we have before. So I just encourage you, there's a lot of other great talks coming up through the summer and through the fall, so come early if you can. So this evening, we're very fortunate to have Darren Larsen from the University of Pittsburgh here with us. Darren, and probably the reason many of you are here, is doing work along the foot of the Teton Range about the Teton Fault. And so that's what you'll learn about here tonight. He has a bachelor's in geological biological sciences from Colby College in Maine. He has an MS in civil, environmental, and architectural engineering from the University of Colorado Boulder, and a PhD from that same university, as well as the University of Iceland. He has a current appointment as a postdoc research associate at the University of Pittsburgh from 2014 until now. And his research interests are in quaternary geology, paleoclimatology, sedimentary systems, global change. You can ask him what he means by global change. Hydroclimate, surface processes, glacial geology, and human landscape interactions, which is, at least in part, what many of us are interested in. He has a long list of both publications and professional presentations. He is, I think, currently working under both a National Science Foundation and University of Wyoming and National Park Service grants to study the Tetons and the Teton Fault system activity. He has a broad research and field experience from Peru to across various western U.S. states, Iceland, Canada, Greenland, and New Zealand. So he's been around, seen a lot of geology, which is always a sign of a good geologist. And I'd like to ask you then to join me in welcoming Darren Larsen.
All right, thanks everyone. Sounds like my mic is working. Everyone can hear me? All right. So I just have to find my top behind this one. All right. Okay, thanks again. Thanks, John, for the introduction, and thanks everyone for coming. It's great to see everyone here. I wish there could be more seats for the folks in the hallway. I will say right off the bat that I'm not going to predict when the next major earthquake is going to be. So if some folks need to leave right now in create some space, now would be the time. Yeah, so as John mentioned, my name is Darren Larsen. I'm a research associate at the University of Pittsburgh. But I'm soon to be moving to California, actually. I just accepted a faculty position at Occidental College, so I'll be moving there for the fall semester. But I'll be continuing to do this research and involving students from Occidental in this exciting research. So the talk that I'll be presenting is entitled Lakes and Shakes, Reconstructing Past Seismic Activity of the Teton Fault Using Lake Sediments at Grand Teton National Park. And before I even get going, while I'm the person who's standing at the front of this room, none of this would be possible without the help from many friends and collaborators and other scientists. There's too many to go through audibly, but I just listed them there. And also, very importantly, the funding that John mentioned here. This work is funded by the National Park Service, in particular through the Boyd Edison Research Fellowship, which is actually through the Grand Teton Association, a University of Wyoming and National Park Service grant, a grant from the Explorers Club, and more recently, a research grant from the National Science Foundation. And before I get going here, if some folks want to read off all those names, I just wanted to ask a few questions of you all to get a sense of my audience here. So how many folks in this room are visiting Jackson for the first time, perhaps on vacation or something like that? No one? So, yeah, you're all locals. people live here full time? Okay, the majority. And then how many of those hands grew up here? How many folks are from Jackson? All right, interesting. Yeah, so I think that says a lot, right? So, and I'll get back to that in just a moment. But to introduce myself a little bit more professionally, I'm a Quaternary Geologist and Sedimentologist. And I'm interested in developing a more complete understanding of the Earth system and surface processes. And so the methods that I employ range from observations and geological data sets that are preserved in sedimentary archives at the Earth's surface. And so the objectives of this research are really to characterize past Arctic and Alpine environments, and those are the regions where I've spent the most time conducting research, to provide a context for current and future changes. The reason I've chosen to work in Arctic and Alpine environments is that these are very sensitive regions that are very susceptible to change, as John mentioned, global change. So any sort of change to the system in these regions results in a very large response that can be recorded in these archives. And so to address questions in this highly multidisciplinary field, I employ a combination of field techniques and analytical skills. And so here's just a Google map image of the world, and all these little ninja stars are places that I have done field work or have ongoing projects. And what kind of the common theme through all of this work is indeed using sedimentary archives to reconstruct aspects of the Earth's climate system or surface processes. Of course, we'll be traveling to the Tetons right out the back door, so that's here in the western US. But on a personal note, like many of you, I'm not from Jackson. I'm an East Coaster. So I grew up in New York State and went to college in Maine, but I then moved to Jackson in the mid-2000s after graduating from college to play in the mountains, and because I was drawn to this magical place, and also to teach environmental education with the Teton Science Schools. So the Tetons have always been a special place for me, but I know that they're also a special place for everyone in this room. And sometimes maybe we forget to ask ourselves why they're so special. And for me, it's really because of this sort of enchanting landscape. And what I'll be talking about today are the drivers of that landscape. What formed the Teton landscape? And in many ways, it all comes back to the tectonic and glacial history of the Tetons. So to place this talk in context, I'd like to say that alpine ecosystems are particularly sensitive to external disturbances related to climate change, tectonic activity, and human affairs. And the impacts of these disturbances on natural environments, they pose serious challenges for human adaptation, hazard assessments, and resource conservation efforts. And so nowhere is this more true than in Grand Teton and Yellowstone National Parks, of course. Now in the Tetons, the very active tectonic setting and distinctive geomorphology and the sensitive position of this region with respect to the climate dynamics of the western US, it presents a very exceptional opportunity for this research. And then in addition, the national park contains a relatively pristine and intact ecosystem that's minimally impacted by human activities. Although of course there is a very long history of human occupation of the Tetons, but I think it's safe to say that there was very little impact of those early settlers of the Tetons. However, despite the importance and sensitivity of this region, few climate or paleo-environmental records exist, and in particular the post-glacial, or past 15,000 years of tectonic activity in the Tetons, this story remains fairly incomplete. And this is not without a whole lot of research that has been done right out the back door here. So there have been numerous investigations and studies that have looked into the tectonic, geomorphologic, glacier geologic, and ecologic history of the Tetons and nearby Yellowstone region. Okay, so the goal of my research here in the Tetons is really twofold. It's to use lake sediment archives to quantify the influences of climate-driven disturbances and changes, and those include the timing and pattern of deglaciation, subsequent glacier fluctuations, moisture balance, and how that's changed, vegetative shifts and fire occurrence, things like that. But also to reconstruct tectonic-driven disturbances and evaluate the influences of earthquakes and earthquake-generated landslides on alpine environments and landscapes, and how those have contributed to the evolution of the Teton mountain range. So this first part here is not really what I'm going to be talking about too much. I'm just starting to publish on this work here. A paper just came out in the Journal of Quaternary Science Reviews that's entitled Deglaciation and Post-Glacial Environmental Changes in the Teton Range as Recorded in Jenny Lake. So this is available online if you're interested in looking into this, or if you're interested, you can talk to me after the talk or email me or something like that. But I'll be focusing this afternoon on tectonic-driven disturbances, of course. That's the title of the talk. Okay, so our Teton Range. This is a Landsat image courtesy of NASA. And it's an oblique aerial view of the Teton Range looking southwest. And so some of familiar features are observable here. Of course, is Jackson Lake, Jenny Lake, and Phelps Lake in the eastern front of the range. Noticeable is this very broad and flat-lying valley of Jackson Hole, and then of course the mountain range, and then on the western side is another basin there. And the Tetons, of course, are fairly linear mountain range, and this has everything to do with the position of the Teton Fault here along the eastern range front. I like this image because it also shows the asymmetry of the range fairly well. You can see how the steep eastern range fronts plunge down into the valley of Jackson Hole, whereas the western flank of the range is much more gradual. And so the Tetons are said to exhibit very high asymmetry with a steep eastern front and a relatively broad and flat, gradual western front. I also like this picture because it shows the range dissected by a series of roughly parallel valleys. These were carved by glaciers during periodic ice ages over the last roughly 2.5 million years. And then at the base of many of those valleys are these moraine-bound lakes. And so these lake systems are what I'll be talking about for the remainder of the talk. But just a little bit of the basics on the Teton Fault. So the Teton Fault is a major range-bounding, eastward-dipping normal fault that extends for roughly 60 kilometers, or almost the entire length of the Tetons. Here's just a diagram here showing, this is off the National Park Service website, showing basically a cartoon image of the Teton Fault. And so you can see the eastern front of the range here in the gradual western slope, and then running right along the base of the eastern flank here is the Teton Fault. And it's a relatively steep, steeply dipping normal fault, where the valley of Jackson Hole is subsiding relative to the mountain block to the west. It's considered to be an active fault, despite no major earthquakes in recent history. The activity of the fault on geologic timescales, or for basically since the Mesozoic, last roughly 10 million years, was paced by basin and range faulting and Yellowstone hotspot dynamics. The total displacement of the fault exceeds the present elevation of the mountain range. It's actually what's fairly debated, but it ranges, general estimates range from between 6 and 9 kilometers of total displacement along the fault, which over that amount of time results in roughly 1 millimeter per year average slip rates. Here's another image of the fault taken from a relatively recent paper by Foster et al. And so here we're looking at a profile of the mountain similar to that diagram I just showed you, but here it's in just slightly more detail. And so on the y-axis here is elevation, and this is distance. So we're looking at a profile, a cross profile of the mountain range. Here's the Teton Basin, the Teton Mountains, and then the basin of Jackson Hole. But it's not just the fault that carved and created the Tetons, of course. The spectacular geomorphology that we can all sort of close our eyes and picture in our minds was shaped by tectonic activity, but also by periodic quaternary glaciations. And so I can toggle here. This is a map of the western US on the upper right, and I put a box around the greater Yellowstone ecosystem and extending southward through the Wind River mountain range. And so of course, this is a Google Earth image, and so this is what it looks like from space right now. But this is not what it's always looked like. In fact, for most of the last 2.5 million years, something like 80% of that time, it would have looked like this. So if you were cruising through space, and you were looking down on Earth at some point over the last 2.5 million years, odds are it would have looked something like this. And so we sometimes forget to realize that many of the landscapes that we appreciate and experience today, especially in the western US and in high mountain regions, were covered by ice masses. And so what I've overlaid here is the Pleistocene extents, or the last glacial maximum extents of glaciers and ice sheets in the western US. At the top of the figure is the southern margin of the Great Laurentide ice sheet and Cordilleran ice sheets. And then you see a series of mountain glaciers and ice caps, of which Yellowstone and the Tetons together are one of the largest. You can see the winds were also covered by a relatively large ice cap. In fact, during the LGM, the ice that covered the Tetons essentially coalesced with the ice cap that advanced southward from the Yellowstone Plateau. So that's important to, that'll tie into this story quite nicely. So the evidence for the presence of the fault on the landscape includes that asymmetry of the range that I mentioned before, with the steep eastern range front that you can see here, and then of course also in this picture taken from I believe the summit of Teton Mountain. And then also those gentle western slopes, but also prominent fault scarps that are visible along the eastern front of the range, particularly those that offset some of these glacier deposits that were deposited at the end of the last ice age. Some interesting data that I'd like to present this afternoon. In fact, I'll be showing many more images that look like this, where it'll be an aerial perspective looking straight down on the Teton Range or whatever feature is of interest, but I'll be showing not the satellite imagery, but LiDAR imagery. And so this is very high resolution aerial imagery taken from basically an airplane. And so in this case, the National Park Service created this LiDAR data set by flying this remotely sensed LiDAR tool, essentially, via an airplane, and they flew over the entire park and the National Elk Refuge. And so we have this amazing data set now. This is available to the public, and it's at 1 meter pixel resolution. So we're looking at very high resolution digital imagery that really brings out some of the topography, which we can then use as evidence to investigate changes in this landscape and those related to faulting. And so this here is, I just overlaid the entire LiDAR data set over the park and the Elk Refuge. And this, you can really zoom in here and have some fun. So this is the Jackson Lake Dam here. This is just a Google Earth image, and then this is the LiDAR here. And so you can really start to see features, including roads, the actual dam, levees, and things like that. Interestingly, though, and importantly, the lake surfaces are just shown as flat. So this LiDAR platform doesn't penetrate into the ground or through the lake surface. So while features on the ground or on Earth show up really well at this 1 meter resolution, we can't really peer into the lakes at all. We just see the lake surface as a flat pan. Here's another great image where I'm showing the mouth of Death Canyon along the southern reaches of the park. And this is Phelps Lake at the mouth of Death Canyon. And so I've overlaid here the lake bathymetry. And so this is showing the basically water depth, or conversely the topography of the lake bottom, where cool colors represent deep water depth and hotter colors represent shallow water depth. And there's some great features here. This is the kind of data set where you can spend hours and hours playing around and zooming over your favorite hiking spots or places to be in the Tetons. And so the lake is, like many of the lakes along the range front, they're impounded by the terminal moraines, or these piles of debris that were deposited by glaciers when the Alpine glacier that occupied, in this case, Death Canyon, was depositing debris that it had eroded at its bed and transported down to lower elevations. So you can see this beautiful nested moraine here as the glacier was essentially sitting at its maximum extent, but fluctuating in response to perhaps changes in climate or mass balance. Also here, showing up beautifully, is the Teton Fault scarp. And so this linear feature here is the fault scarp, and you can see it beautifully offsetting these Pleistocene moraines. I'll talk more about that in just a bit. But I zoom in here because to really show off this data set, of course it's not mine, but I think it's so great to show off. So these little white dots are individual rocks. This is the trail that leads into Death Canyon. Many of you probably have hiked, at least when the parking lot used to be to the north of the lake there. You used to hike down these switchbacks to access Death Canyon. Of course, at the end of the day, these were miserable, very hot. You can see the inflow stream here and the inflow delta on the lake's western shore. It's just incredible. And so while the fault has been active for millions of years, my story really checks in at the end of the last glacial period, or since the demise of the valley glaciers that occupied the Tetons. And that was roughly 15,000 years ago. Because what I'll be doing, or demonstrating, is that we can use lake sediments deposited in these lakes to reconstruct the faulting, which you can clearly see here, offsetting these glacier deposits. So much of what we know about the post-glacial or relatively recent fault activity has been gleaned from this prominent fault scarp that I'm sure many of you have seen. And if you haven't, I encourage you to simply drive up and look for it, offsetting these glacial moraines. It's clearly seen here in the LiDAR imagery running north to south, right along the range front, and indeed offsetting these moraines. And so these scarps are beautiful, and in cases they're up to 30 meters tall, or over 100 feet tall. And they displace these Pinedale age, that's the term for the last glacial period, these Pinedale age deposits, and they suggest a relatively fast slip rate of up to 2 millimeters per year. And again, this is a very long-term average. This number was just determined by taking 30 meters and dividing it by roughly 15,000 years. So you do that simple math and you come up with a number that's roughly 2 millimeters per year. Of course, folks have spent a lot of time doing some more detailed calculations of the fault slips, and that is indeed still a very active, ongoing field of research right here in the Tetons. But this average slip rate is sort of misleading because this offset did not occur in a very gradual manner. It's not like our fingernails growing or something like that. It occurred through a series of very major and catastrophic earthquakes. And the post-glacial paleoseismic record of this fault has been pieced together through quite a large body of previous work from a few different, very independent sources, and it's very interesting. I'll walk us through that. But I would say that it remains incomplete. One line of evidence that we have for post-glacial faulting are interpretations of paleo shorelines in Jackson Lake. And so this is not Jackson Lake here. This is from somewhere near the coast in the Gulf of Mexico. Totally unrelated, but it's a picture showing a series of paleo shorelines. So this is high-resolution bathymetry data. Again, cool colors represent deeper water depths and warm colors are shallower. And what it's showing you here is that there's a series of paleo shorelines where as the water level in this basin fluctuated, it left shorelines that are now submerged, but they can be seen with this bathymetry data. And so Jackson Lake has a series of paleo shorelines. I've never seen them, but this is summarized by a field guide by Ken Pierce and Good in the early 90s, where before they built the dam, it was known that there's a series of these submerged paleo shorelines that were essentially created by each time there was a fault, the basin, the water in the basin essentially shifted towards the fault and submerged what used to be the lake shore. And so there's roughly 8 or 10 of these submerged shorelines, and if the consensus is that they were formed during a major fault rupture, which resulted in a few meters of displacement, and the water shifted towards the fault, it would submerge the previous shoreline and create a new shoreline a few meters above that. And so from that, the best research suggests that there have been about 8 or 10 major earthquakes since deglaciation, or since Jackson Lake was basically born, since the glaciers that were occupying that basin melted away. Now, archaeological remains found on those shorelines imply that earthquakes occurred at basically evidence for 2 earthquakes, one that occurred between 3 and 5,000 years ago. So KA, I'll be using that abbreviation a lot, that just means 1,000 years ago. and then another subsequent earthquake between 1.5 and 2,000 years ago. So there were people occupying the shoreline area around Jackson Lake. And when after an earthquake, the lake shifted, of course, and so the folks who were perhaps living there or spending time on the shore could no longer be in that area because now it's covered by water, but their remains were left on the landscape. They're preserved under the water and they can be dated. So that's one line of evidence, these interesting paleo shorelines. Another terrific line of evidence comes from a trench study that was trenched right through the Teton Fault near the mouth of Grand Canyon. And the trench studies are really the closest the closest data sets we have to essentially empirical or direct evidence for faulting. Because here we're looking at offset layers. And so radiocarbon dates from a trench that was dug perpendicularly through the fault scarp at the mouth of Grand Canyon suggest two other major earthquakes, large earthquakes that produced roughly 3 and 1 meter of vertical offset, occurred at roughly 8,000 and roughly 5.5 thousand years ago, respectively. So this is done, a lot of this work was done by Robert Smith at the University of Utah and his graduate student at the time, John Bird. I know Bob Smith is a denizen of the valley here, and I'm sure many of you know him personally. So this was terrific and pioneering work, absolutely. Based on this trench study and the magnitude of displacement, Smith et al. Reckoned that these earthquakes are the amount of displacement require major earthquakes, magnitude of roughly 7, so Hegben Lake-sized earthquakes. This is a diagram taken from the paper showing it's a detail of that trench. We're looking at one of the sides of the trench, and so here's the Teton Fault. Of course, this is not it doesn't look anything like this textbook diagram here where you have a perfectly uniform bed that's been offset, and so if you can date organic material in that bed, then you know the timing and the offset. Of course, it's a relatively messy system. There's streams coming out of Granite Canyon, bringing with it sediment, colluvium, and floodplain deposits, things like that. So it's certainly not easy to do this work. It's difficult, but it's really some of the best, and it was the pioneering work on the Teton Fault at the time. And so we have the paleo shorelines of Jackson Lake and the trench study at Granite Canyon. And then some folks have tried their hand at computer model simulations of the fault itself based on this empirical data set. And Hamp et al. In 2007 and subsequently in 2010, they reasoned that they used that trench data and this idea that there was roughly maybe 10 major earthquakes of the fault to suggest that there was a relationship between the timing of faulting and the timing of deglaciation. And so they reckoned that if the displacement near the trench site is 15 meters, and we had roughly 4 meters total displacement at the trench, then that other 11 meters must have been accomplished before 8,000 years ago, or essentially the earliest earthquake that was recorded at the trench. And so they suggest that the majority, or 70% of the offset, occurred before the earliest rupture recorded at the trench. And so that hints at this relationship between regional deglaciation and the fault slip rate. And so through model simulations, focused both here and in the Wasatch and in Scandinavia, they demonstrate that as you unload the crust, as you melt glaciers and ice caps at the end of the Pleistocene, there would be a propensity for isostatic rebound, which would induce faulting and a postglacial slip rate increase. They show, this is taken from their paper here, showing a roughly average slip rate, and deviating from that line, you can see here at the end of the Pinedale this major increase in slip rate. Okay, so with all of this previous work in mind, I developed 2 major research questions. The first one is there a complete record? So we have this evidence from the paleo shorelines and from the trench study, but that's of course incomplete. Both of those lines of evidence demonstrate the possibility of 2 large earthquakes. And so I'm wondering if there is a more complete record on the landscape that can be targeted to develop a complete or continuous and also well-dated record of earthquake events at Grand Teton National Park. And if so, can we exploit these records and from them determine the timing and frequency of major earthquakes? With these research questions in mind, I developed a relatively general hypothesis here. And this is based on some preliminary work studying lake sediments from lakes positioned along the range front. And so my hypothesis is that these major earthquakes at Grand Teton National Park generated different types of slope failures. So if you can imagine, we're talking about very large, intense earthquakes that could potentially generate slope failures of various kinds. And so the three slope failures that I predict would be generated by large earthquakes are lake-inflow delta failures. And so this is the inflow delta, which is generally here in the Tetons on the western side of the lake. And as sediment is brought down these valleys, it's deposited right here as the stream enters the lake. And so these are relatively steep deltas. And so I predict that during a major shaking event, this unconsolidated delta feature, comprised of sand and silt and clay, would fail. And so that sediment would be deposited downslope away from the deltas into the basin. Also, I predict that major shaking events, basically following kind of the similar logic, would induce subaqueous gravity flows. And so in this case, sediment that was deposited in the lake previously during a major shaking event would get reworked and mobilized and deposited elsewhere. And that would have a distinct signature. And then I also hypothesized that past earthquakes would cause landscapes on hill slopes outside of the lake, so above the lakes. All of these hypotheses are centered around this idea that each one of these disturbances would be deposited and recorded and then archived in the sediment sequences contained in these lakes. So to test this hypothesis, we set out to identify and date a suite of slope failure deposits that, of course, we had already recognized in some of these cores, from multiple lake basins positioned along a broad section of the fault. And so we've set out to core many of these range-front lakes, including Phelps Lake, Taggart Lake, Bradley Lake, Jenny Lake, and we actually don't have any cores from Lee Lake yet, but it's a similar system. And so the idea being, while we might be able to demonstrate this in one lake, it's the power of this really to reconstruct the fault history is if we can demonstrate these features in multiple lakes along the fault. Because if you identify what seems to be any one of these features or some other anomalous deposit in a single lake, that could be caused by numerous other sedimentation events unrelated to fault activity. For example, major flooding events or fire-induced landscape erosion, things like that. So I touched on this briefly before, but the unique tectonic setting and glacial history of the Tetons has created a series of these roughly parallel east-west trending U-shaped valleys that are carved into the steep eastern front of the range. And so this is an oblique satellite image here showing Cascade Canyon with Jenny Lake at its mouth, and then to the south here, this is Avalanche Canyon, and of course other canyons in between. Interestingly, many of these valleys contain a chain of lakes that were formed as ice retreated from and melted away from each individual valley at the end of the last ice age, around 15,000 years ago. And so the sediment fill in each lake marks the timing of glacier retreat, which is coincident with the birth of the lake, right? Lake inception. And it contains a continuous and datable record of past environmental conditions, including seismic activity. Below here, I've just shown, this is an aerial view of Avalanche Canyon, showing one of these textbook chains of lakes. This is Taggart Lake, positioned behind those beautiful moraines, right by the parking lot there, which are exposed really nicely now following that fire a few decades ago. And then up valley, you have a suite of lakes up valley, Lake Tamina and Snowdrift Lake. And so I put together just a little cartoon conceptual model to demonstrate how these lakes have formed and begun to accumulate sediment since their formation, and how that sediment is still preserved today and can be recovered to to answer some of these questions. So this is potentially what a cross profile will say of that canyon, maybe Avalanche Canyon here. This is what it looked like during the Pinedale maximum, for example. And so we had a valley glacier, in this case, streaming down to the valley floor, depositing this terminal moraine. Maybe there's multiple moraine crests that are nested together as the glacier fluctuated slightly near its maximum position. And then during the latest Pleistocene deglaciation, the valley glacier, in response to changes in mass balance, began to retreat up valley. And so it uncovered the moraine-bound Piedmont Lake on the valley floor. Now, as soon as it uncovered that lake, of course, sediment delivered by meltwater emanating from the glacier was deposited in the lake. And so this would have been a proglacial lake. Perhaps there was rapidly accumulating sediment at the lake bottom. Now, as the glacier continued to melt up valley, it exposed another lake. And this lake is now accumulating sediment. And this, of course, happened until today, where there are essentially no major glaciers occupying any of these valleys, other than some small cirque glaciers and perennial ice fields. And so what I'll be talking about is the sediment archive deposited in these large moraine-bound lakes, which contain this datable sequence of glacier deposits and then subsequent non-glacial sedimentary deposits. And so to study these sediments, we employ both seismic surveys, so these are completely non-destructive surveys where you are using a seismic profiler. In this case, it's a lightweight towfish that emits an acoustic ping, and that ping is transmitted through the water column, but also through the sediments below, and then it is reflected back to a receiver, and from that you can actually map the distribution and thickness of sediment contained in these lakes. In this case, this is Jenny Lake, where we performed a seismic survey in early October, thinking that, of course, it'd be still nice weather, but we ended up performing the survey in really choppy, wintry water here. So this is field assistant Devin Hogarty, who was at the University of Minnesota at the time, and he's driving this towfish, essentially, tweaking the knobs in response to changes in bathymetry and sediment thickness. But then, of course, we also need core data. We need the actual sediments. And so to do that, we'll ski out or walk out, depending on the conditions, on the frozen lake surfaces and auger a hole to core or collect a sample of the sediment fill. And so this is a crew of scientifically inclined researchers skiing out onto Jenny Lake. And you can see here all the equipment necessary. We've got ice augers, we have empty core barrels and tools and things like that. And yeah, oops, that's a little bit out of place, but we don't have to be working on frozen lake conditions. It's much easier to work in conditions like this, of course, because you can really spread out all of your equipment and you don't have to worry about getting wet. But we've also done some coring in the summertime. This is a coring expedition up on Delta Lake as part of a separate project to reconstruct the history of the Teton Glacier. And in this case, we put together an as lightweight a coring setup as we could manage, because of course the hike up to Delta Lake is non-trivial. And so here we're coring off some pack rafts with a pretty rickety platform that we put together. And we're collecting sediments from Delta Lake, which are produced by the glacier. So those sediments contain a history of the Teton Glacier.
Darren, how do you get that pipe thing down deep enough to?
Yeah.
You've got a lot of rocks and things.
Yeah, that's a great question. So there's there's different types of coring systems that you can use, and the type of system is really that you would prefer is really dictated by the water depth and by the amount of sediment you're trying to capture. And so in this case here, Jenny Lake is extremely deep, right? I'll be telling you exactly how deep it is, but it's roughly 255 feet deep at its deepest. And so of course you can't lance drive, or you can't push rods with a tube at the end into that sediment. It's just unrealistic, it's too far. And so in this case, we deploy the core barrel on cables, which we lower down through the hole we've augered in the ice, and then we hammer that tube into the mud. In this case, on Delta Lake, it's relatively shallow. Delta Lake's only about 25 feet deep. And so here, we've got a similar core barrel, like one of these, attached to the ends of these rods, which these are carbon fiber rods, so they're extremely lightweight and transportable. And we just keep attaching rod lengths, screw them together until we reach the sediment, and then we can push in to the mud at the bottom. And then it's sort of like putting a straw into a smoothie and putting your finger over the straw and then pulling it out, and you've got the smoothie in the straw. It's a very similar concept to that. It's great. We might as well get into it a little bit more. What's nice about this system is that it allows you to re-enter the same exact hole that you just took a core from. So in places like Delta Lake, where the sediment thickness in the lake is very hot, very thick sediment package in the lake because there's so much material coming into Delta Lake. That's why, of course, it has this really characteristic milky hue, this glacial flour, which is just suspended sediment, fine-grained sediment, that's suspended in the water column until seasonal ice cover, when it can settle through the water column, when the wind is no longer turbating it, keeping it suspended. So there's a very thick sediment package in Delta Lake, and so you can't get that in a single drive. You can't push one core barrel into it and get the entire package. And so what's nice about this system is that it allows you to re-enter the same hole and take out successive, in this case, 1 meter drives. Whereas on Jenny Lake, you can't really do that without some larger equipment that we actually did just haul out this past winter. But in general, you can't do it with a lightweight system like this. And so here, because you can't enter the same hole, but you want to get the full sequence, in this case, we just pound down the longest tube we can find, which in this case is a piece of aluminum irrigation piping that we picked up in Nebraska on the drive out here. And so we cut a 5 meter long section of aluminum irrigation piping and then hammered that entire roughly 18-foot tube into the mud and then jacked it out with a handy car jack, which you can see right here, because of course you couldn't pull a 20-foot core right out of that lever. That's a great question. So we hammer it by suspending the cable that's connected to that pipe, which of course is now 200 feet below their feet, and you hammer it into the mud by attaching a cylinder weight that's basically sitting on top of the core, and then has these ropes attached to the top of that weight that are attached to these pulleys. And so these folks here on either end are simply pulling up on a weight and then letting it drop, and pulling up on the weight and letting it drop. And so it pounds the tube into the mud by just dropping this weight on the surface of that core. It takes quite a long time, because you get, with each hammer blow, you maybe get a few millimeters. So we're out there all day. By the end of the day, hopefully you've got your tube full of mud and you can pack up before it gets dark. But that doesn't always happen. Sometimes we're out there at night, because in general, once you start, it's good to kind of finish the job. All right, so we've done that at many of these lakes along the range front. What I'm showing you here is again that same picture of the eastern front of the range, but I've overlaid the fault trace running along. And what's imperative here is that the lakes, I should say, are sitting right on the fault, basically. The fault is running right along the western boundary of many of these lakes. In some cases, it looks like it goes right across the lake basin itself. And it also just barely goes through Jenny Lake, as I'm about to show you. This is now just a zoom in of this red box of Jenny Lake at the mouth of Cascade Canyon. Here I'm showing that nice LiDAR data set. North is to the right here, so we're kind of peering down over the lake. You can see these Pleistocene moraines impounding the lake. I'm showing the lake bathymetry here. You can see the deepest portion of the lake is right in front of the canyon mouth as the glacier excavated that region. And then I've overlaid here the trackways that we drove with that seismic sub-bottom profiler. So this is our seismic survey here, which we conducted in a relatively gridded manner. And then these white dots are locations of sediment cores. So I'd like to use Jenny Lake as kind of a study site to demonstrate some of this work. So Jenny Lake is sitting at roughly 2,070 meters above sea level. It's about 5 square kilometers in surface area at its surface, and its maximum depth is 75 meters, so roughly 255 feet deep, sort of close to the western boat dock, western boat launch, for those of you who have hiked around the lake or perhaps taken the Jenny Lake boating tour or transport across the lake. So the existing glacier chronology suggests that essentially Jenny Lake was born roughly 15.1 thousand years ago, and that there was relatively rapid up-valley retreat with 90% recession accomplished by roughly 14,000 years ago. Now both bathymetric data, so this is not my data, this is National Park Service data, the bathymetry here, but both the bathymetry and the seismic data that I'm about to show you reveal a very complex lake floor morphology related to the glacial history, but also to tectonic activity. On the left here is this familiar map of the lake. Here I'm only showing 2 seismic trackways. So A to A prime, running from the canyon mouth to the distal shore here, and then B to B prime, running roughly north-south. And these seismic trackways are shown in the 2 panels on the right. And there's a lot of very interesting features that are shown by these seismic tracks. I've also highlighted on the map here the fault trace as it's identified in the LiDAR imagery. And then these blue stars with arrows are what I believe to be landslide head scarps and runout paths, both of which ran out into the lake basin. In fact, you can see here this kind of dashed blue circle is highlighting this lump that you can just make out in the lake bathymetry. I would like to say that this lake bathymetry, while it's a terrific data set, it's relatively coarsely resolved. And so this is just a smoothed representation of what the lake floor actually looks like. Of course, we're looking, the LiDAR, for example, is 1 meter pixel resolution. This is probably something on the order of tens of meter, if not maybe even more. This was the focus, actually, why I was out just last week doing field work here on Jenny Lake, and we were sailing around with a multi-beam sonar system to collect bathymetry data at the same resolution, if not better, than the terrestrial LiDAR. So we've just collected extremely high resolution bathymetry data of Jenny Lake, and we're processing that data now. And so we'll be able to map the bathymetry of the lake at higher resolution than this LiDAR data set. And so it'll be really great to marry these 2 high resolution data sets. Okay, but I digress here a little bit. So these are the seismic trackways here. I also want to point out the locations of a few core sites. So core site 1 and 2, and I've shown where those are located on these seismic tracks. So if we first focus on this east-west profile, we can see how essentially the delta front here is very steep, and the bathymetry, the water depth increases rapidly as you approach that central deep basin. But I also point out the position of the Teton Fault. So this is actually the fault scarp offsetting conformable lake sediments that you can see with the seismic data here. And so this is a continuation of this fault trace running through the lake bottom. So this is extremely interesting. You can see how these, so I should get into it a little bit here and say that the sub-bottom profiler is an acoustic system. And so the way it works is that changes in the physical parameters of the sediment will influence the way the speed of sound or sound waves travel through the sediment fill. And so opaque reflectors here indicate a change in perhaps density or grain size, something like that. And so you can trace these reflectors across the basin. What's interesting here, and so each reflector is essentially an isochron. It's a continuous surface of sediment that was deposited at the same time throughout the lake. What's interesting is you approach the fault here, you see these reflectors start to diverge, which suggests an increase in sediment accumulation rate in that location through time, perhaps generated by faulting and increasing accommodation space, or sediment streaming from higher up on the delta front. So that's really interesting. I also highlight this topographic high here, which I'm interpreting to be a glacial moraine, perhaps a recessional moraine as the glacier exited the lake basin. Of course, it didn't happen uniformly. Perhaps it did, perhaps it didn't, but it looks like there may have been small still stands or re-advances during the overall phase of retreat. The second panel on the right here, I'm showing this north-south transect from north to south. And what I'm highlighting really in this seismic profile is this massive deposit of unconsolidated debris. And so that's right here on the seismic profile, right next to this little lump that you can see in the existing bathymetry, and which of course is directly below this headscarp on the hill slope here of what is essentially Teton Mountain. So that ran out, I predict this is a landslide that ran out here, and you can also see how it is basically transecting this Pleistocene moraine. You can follow the moraine right to about here, where it's essentially been washed out due to this landslide. Yeah, question?
Were any of these features we discussed present prior to the landslide stage?
So the question was, are any of these features here, for example, this landslide deposit, or what is potentially a glacial moraine here, or even the sediment that we're looking at, present prior to when the ice occupied the basin? And I would suggest, or I would argue that no, they were not. So the glacier that was occupying this lake is extremely erosive. And so I'm working under the idea that basically anything in its path is being bulldozed away, and that the glacier was probably in contact with a bed of previous outwash or quaternary sediments that were occupying the basin, perhaps those deposited during the last interglacial or during some point during the Pinedale Glacial. And so these features, none of this sediment, which you can see clearly here or here, was present when the glacier was there. That's all been deposited since the glacier retreated. It's a great question. But this is fantastic.
You used the term landslide there. Can you resolve whether or not it was an avalanche or a landslide at all?
Do you mean a rock avalanche or a snow avalanche?
Snow avalanche.
Yes, so it's very, so the question was, how do we know that this is a landslide or perhaps another type of deposition event such as an avalanche? Of course, I don't have any pictures of it right now, but if you looked along this hill slope, you'd see active avalanche paths. And if you, in the wintertime, perhaps like to ski out to Jenny Lake, you'll see that there's major avalanches coming down these runout paths, which are essentially on the same hill slope. And you'll see, tree stumps and piles of snow right on the lake surface. Sometimes the stumps will be sticking right out of the ice, as what happened last winter. I don't know if any of you were up there at that point. But no, this is most likely not an avalanche deposit here. This is a fairly large headscarp. It's about 20 feet tall, and it's down to bedrock. So the scarp itself is bedrock. This is not a surface avalanche process. This is a part of the hillside broke off and fell and all slid downhill. So this is not a snow avalanche, but I would say that snow avalanches occur. For reference, the size of this debris pile is huge. It's something on the order of 10 meters tall, and this is maybe 400 meters long. So this is a massive deposit of debris that occurred. In this case, this one pile, you can actually place ages on it by following the reflectors that stream off from the profile. So following the sediments that have this distinct opaque reflector, and the idea being that we can put ages on the timing of that deposit by coring through that sediment sequence and dating that reflector, what in the core corresponds to that reflector. We've also dated a series of, and I'm not going to show this data today, perhaps we can talk about it tomorrow. We've actually dated the bedrock and boulders in the runout path using cosmogenic radionuclide techniques, beryllium-10 exposure age dating. And so we're very confident that this is a landslide. And you can see it right here in the lake sediment. Okay, so how do we date these sediments? Some of you, I'm sure, are familiar with radiocarbon dating. And so all we need for that are relatively small pieces of organic material that's been incorporated into the sediments. So here's 3 images of Jenny Lake sediments representing a few different cores, and in this case, different time periods. And so our 3 main lines of dating, or methods in which we establish chronologic control, are through radiocarbon dating of organic material, but then also tephrochronology. And so in Teton Lake sediments, there's a series of 2 very diagnostic tephra layers that correspond to the eruption of Mount Mazama around 7,500 years ago. That is when Crater Lake blew its top. And then the glacier peak ash, which I'm showing here. This is from Glacier Peak in the Cascades. And this is actually a series of relatively large eruptions that occurred over the span of a few hundred years. But one of the largest marker beds in this region has been dated in many sedimentary archives to around 13.6 thousand years ago. So we can use that in conjunction with radiocarbon to establish age control. And then as we get deep into the sedimentary sequence, we are in the glacial sediments, and these are annually laminated glacial sediments. And so we can actually just do layer counting here. What I'm showing on the bottom is the chemical composition of these 2 ash layers. And so we can identify the tephra layers based on their major element composition.
Did you identify any radiation?
From these eruptions?
Yeah.
No, but we haven't looked for it. No. We do look for radiation. We look for cesium peaks from nuclear arms testing in the recent past to date, very surface sediments, very recent sediments, but no, we haven't looked for any radiation down here at this depth. Okay, so back to those 3 hypotheses where I'm hypothesizing that major shaking has induced delta failures, gravity flows, subaqueous gravity flows, and then landslides. So this concept here has been demonstrated in lakes around the Lake Tahoe region, where there's also very active faulting. And so they've looked at lake sediments there and demonstrated that there are these sequence of disturbance deposits related to slope failure within these lakes. And so this work is basically using the same techniques of combining seismic stratigraphy with lake cores. And so if you can core through this seismic data here, or core through the sediment sequence that you can see visually with the seismic imagery, then you can identify what each of these units that's visible in seismic stratigraphy, you can put ages on those using those dating techniques that I just showed you. And so here's a close-up view now of the inflow delta of Jenny Lake. And so this is Cascade Creek. So there's 2 inflows to Jenny Lake. One is to the north from String Lake, and the other is to the west down Cascade Canyon. Because String Lake is more of a flowage, and it actually acts as a sediment trap, it doesn't deliver very much sediment to Jenny Lake. That's why there's not really a delta there on the lake's northern inflow. Most of the sediment to the lake is likely coming from Cascade Canyon. And so this is the delta here. You can see a few features. This is a relatively small delta, and it's very steep. And so this water depth drops off to hundreds of feet in a span of a few tens or maybe 100 meters or less. It's amazingly steep. So that sand and sediment that's comprising the delta is really just sitting there at its angle of repose. And so the idea is, if there is an earthquake, it's likely that that delta will fail, and sediments will stream down slope and be deposited and look something like this. And so we just took a core this past April from right in front of the delta fan, and we haven't even opened the cores yet. That's what I intend to do on my drive back the day after tomorrow. The cores are resting at the National Lake Core Repository in Minnesota. So I'll be driving back there to open these cores, but so the results are pending. The next type of disturbance, though, which we do see in many cores from both Jenny Lake and other lakes, are these disturbance horizons. So I'm just showing here a collection of what these look like in core section. If you'd like to follow me around here, on the right is this very strange layer from a core taken in the central basin of Jenny Lake that has coarse quartz sand. So a coarse lens of quartz-rich sand and organic material incorporated in it. Deeper down in that same core, you'll see another disturbance deposit that looks somewhat similar. It's coarse sand that finds upwards to a clay cap. And then I've shown a few examples of this from another core closer to the delta, where you see extremely coarse sand that finds upwards to a clay cap. And you see a regular series of these. This got cut off because it was a core break. But we have a series of these disturbance deposits that all look very similar in nature, and due to this grading upwards pattern, suggest a rapidly deposited or a rapid deposition event. We also see these unconformities in cores that were taken from slopes in the lakes. So this was a core taken from the back slope of a recessional moraine in Phelps Lake, and you can see this very old minerogenic clay and silt-rich sediment that was deposited during glacial times when there was a glacier in the catchment. So we know based on many lines of evidence that that is at least 12,000 years old. And then we see this extremely sharp contact. It's been smeared a little bit because I was taking a smear slide to it, trying to pretty it up, but it didn't work so well. But you can see this really sharp contact to relatively young, very non-glacial, organic-rich sediments. And if you date some of this organic material here, it's much younger. So this particular core, I dated a macrofossil up here, and that's around 5.3 thousand years ago. So we know based on this that this is non-conformable, that something happened roughly 5,000 years ago, or slightly prior to 5.3 thousand years ago, that induced a slope failure, which basically chopped off the upper part of the sediment sequence, and then sediment was deposited right on top of that failure surface. So that's very interesting. And then here, this is a core from Bradley Lake, showing how there's a series of these high-density, low organic matter silt horizons in the lake. And so there's just there's many of these, and I just wanted to show them in graphical form, how you can track these events using physical parameters of the sediment. And the third slope failure is this landslide, which I just spent some time talking about, so I won't talk about too much anymore. But this is this massive landslide that we see in the center deep basin of Jenny Lake. But there's also one to the north here. And so here, the close-ups of those two landslides. This is a deep landslide that produced quite a lot of sediment. I actually think, based on recent evidence, that perhaps this was activated multiple times during successive earthquakes. But then there's also this relatively shallow and broad headscarp here that you can see breaking off this moraine coming down from a hanging canyon, and then cross-cutting this left lateral coming out of Cascade Canyon. So this broad sheet here looks to be another headscarp and landslide scar. Interestingly, at the base of this landslide scar, there's a submerged forest, so to speak. So there are trees. This is wild. You can actually see this if you kayak around Jenny Lake, because you can see the tops of the trees from the surface. But there are a series of upright, potentially in situ trees in about 80 feet of water. And so some folks from Peter Stalker and the search and rescue, I think they frequently practice search and rescue techniques, underwater rescue in Jenny Lake. And so I asked them to take some footage of these trees. And here you can see the base of one of these large trees. Here's a few trees sort of lying down at an angle. And here's another tree that's just shooting straight up to the surface. And so it's possible, it has been previously hypothesized, that these trees were deposited due to a landslide event. There are other possibilities for getting those trees in that location, but we can discuss them later if you're interested. So if you combine all of these different lines of evidence, these disturbance deposits and landslide events, you can kind of make a list of and then date those deposits. You can make a list of major disturbance events that seem to be coincident across lakes positioned along the Teton Range and along the fault trace. And so what I've done here is I've made a list of what I'm considering major disturbances based on the very large expression in the sediment core data, and then just the lakes that I'm finding them in, which line up with each other. And so here's a list of what I'm suggesting are past earthquake events in chronological order. So roughly 5,500 years ago, 8.3 thousand years ago. You'll see most of these are in Jenny Lake cores, but some of them are corroborated by other lakes, such as Phelps Lake and Taggart Lake. 9,000 years ago, 10, 10.5. There may be a gap here, 12.7, and then roughly 14.5 based on layer counting of VARs. So this is based on preliminary cores, not the major coring effort that we just performed this past spring. Then I have a list of what I'm calling minor disturbances. These are, in the case of these trees, the age of these trees, and I'm calling them minor because I can't for sure say that those were deposited by that landslide, but I'm just saying potentially. But it's also corroborated by this unconformity, a disturbance layer in Phelps Lake, and then 2 other disturbance deposits at 1.7 and 3.6. Now, if we line these up with the existing data, it's pretty exciting. So the most recent major disturbances in Jenny Lake line up within the dating uncertainty with the ages of the trench dug in Granite Creek. And then 2 of these more recent disturbances that are seen in Phelps Lake and in Bradley Lake seem to line up within the age uncertainty of the paleo shoreline ages from the archaeological evidence on those paleo shorelines in Jackson Lake. So this is very encouraging and really exciting. So with that, I'd like to summarize here and kind of wrap things up. So the spectacular geomorphology of the Tetons attracts millions and millions of people each year, visitors to Grand Teton National Park, and it's attributed to active uplift along the Teton Fault. So this spectacular scenery is attributed to the uplift along the fault. Previous studies suggest that these prominent fault scarps that are visible all along the range front were generated by a series of major earthquakes during the past 15,000 years, but the paleoseismic record is relatively incomplete. And so while this alluring scenery has benefited from this tectonic activity, the potential for future large earthquakes and related slope failures presents hazards to all of these millions of visitors, to infrastructure and resource management efforts. So what I'm proposing here with this study, which again is certainly in its emerging stages, is that lake sediments in the Tetons preserve past earthquake events and present an exceptional opportunity to construct a continuous and well-dated post-glacial paleoseismic record of the Teton Fault. And with that, I'd like to say thank you and take your questions.
We have a few minutes for questions for Derek. Surely somebody has a question. Yeah.
In comparison to, you're doing your study on this side, on the east side, what would happen on the west side, or would there be anything on the west side that might show something to it? It's not as steep, so there wouldn't be any landslides and stuff.
Yeah, I know folks are collecting sediments.
Yeah, you might repeat the question, Derek.
Yeah. So the question was, generally was, have we been comparing these records coming out of the eastern range front lakes with lakes on the western slope? And the simple answer is no. I do know folks are coring those lakes primarily for archaeological purposes, but I think those sediment archives, or those cores exist, that could certainly be compared. Again, the beauty of these lakes here is that they're sitting right on the fault scarp, and they're positioned below these steep hill slopes. And so major ground shaking results in these slope failures, which are then deposited in the lake. Presumably during large earthquakes, of course, those lakes on the western slope would be shaken, and so you might have some sort of liquefaction layer or disturbance deposit that could be identified. So absolutely, I mean, the potential's there, it just hasn't been done. Yeah.
Where can you see that LiDAR?
where can you see the LiDAR data? If you Google, so there, on the USGS website, you can download a KMZ file, which you can just load in Google Earth, which is of course also a free download. So if you Google, first make sure you have Google Earth. So Google Earth and download that. Next, I would Google just something like USGS Teton Fault LiDAR, and it'll direct you to a website where you can download a KMZ file that has the whole swath of the Teton Fault extending from Jackson Lake all the way down to Teton Pass. And that's great. The entire park data set I don't think has been converted to a KMZ or like a very usable file yet. I would imagine that's an objective of the park office, but they have that data, and if you're interested, I mean, it's gigabytes large, and you need to kind of play around with it, massage it in ArcGIS or some similar program, but it's available, so I would perhaps contact them if you're interested in that. But the fault swath is, I mean, you could download that on your iPhone. Yep.
I think over at like top of the tsunamis that after Earth sliding
Yeah.
anything like that here.
Yeah, absolutely. So the question was, do we see evidence for any sort of tsunami or perhaps a seiche wave, where if after a large landslide or a rupture of the fault, do you see a major seiche wave in the basin? And so the answer is yes, I think we do. Again, this high resolution bathymetry data, I think, is going to show some of these deposits in really high resolution. So I can't wait, maybe next year I'll be able to present that or something like that. But I think we'll be able to see these deposits in the bathymetry, but we have cores from near the back slope of the impounding moraine. This moraine, the back slope of the moraine is really steep, and it's really tall, 140 feet tall. And so this core that's positioned near this back slope here, I don't have a picture of it, I could dig it up, but it basically terminates, it terminates in glacial sediments, but before you get there, there's this massive deposit of boulders. Like, it's amazing we cored through them. They're grapefruit-sized rocks, and that is also normally graded. And one of the rocks is a piece of quartzite, is a quartzite cobble. And so there's no source for that quartzite cobble up valley. That is most definitely coming from, or most likely coming from the moraine itself. And so the way I interpret that sequence is that there was a large wave generated by either a large landslide or rupture of the fault. It generated a seiche wave, which induced failure of this. You can see here the back slope of this moraine, and material from the moraine was deposited at the core site. It's really, really cool.
Do you have similar data to that in Jackson Lake?
No. The question was, do we have similar data in Jackson Lake? And so I know folks have mapped the seismic stratigraphy of Jackson Lake. I also know that people have cored the lake. I have not. Presumably it exists. Again, you want to be targeting regions that are near slopes and near potentially the fault itself. Much of Jackson Lake is a little bit different in that it has been overridden by the southern margin of the Yellowstone ice cap. It wasn't really formed by this valley glacier system. So it's slightly different. I would imagine, I know that Robert Smith and others have spent time studying the seismic stratigraphy of Jackson Lake. So it would be an interesting comparison. Yes?
Have you given thought as to the size of the seismic events that produce these?
Yeah, so the question was, can we say anything about the size of the events based on, for example, the size of these landslides, the amount of offset that we can see in the seismic stratigraphy, or perhaps the size of the disturbance deposit? I would say yes. I know people certainly can look at the size of a landslide and from that determine the estimated magnitude of shaking, basically, that would have caused that shear, that fracture of that rock, but I have not looked into it myself.
I mean, you have some constraints already. You know you have an event that's tagged in both Phelps Lake and Jenny.
Right.
They're separated by, 10 kilometers?
Yeah.
So the moment magnitude relation would give you some idea of the slip and the area that you.
Right. So so what was just stated, for those of you who couldn't hear, is while instead of using the actual disturbances in a single lake, if we can just say that a major disturbance was felt in 2 different regions separated by a certain amount of distance, we can then say something about the size or the magnitude of the earthquake, if it affected a region this large. I think there are a lot of things that go into that, but yeah, absolutely, you could get into it.
The Smith et al. Paper, did he talk about the higher range front for this magnitude 7, the higher range front fell and that sort of?
Yeah, is Robert Smith here?
Bob's not here today.
Because he could certainly.
But it probably was. I mean, you're talking about tens of kilometers.
Right, so I would agree with you, but in that paper and in subsequent papers, they've showed that the amount of displacement varies significantly across the range. So that would indicate that maybe, there's different responses to an earthquake generated at a certain location along the fault. Yeah, or segments, yeah. Great question. Yes?
Once the landslide starts, what is the approximate time frame from inception to completion of the process?
In this case, I would say it's extremely rapid.
You'll have to repeat that.
Oh, sorry. I believe the question was, what is the speed of transport of the landslide, of the material?
No, well, the time frame from inception to completion once the landslide starts.
It's essentially instantaneous. It's like watching a snow avalanche. As soon as it initiates,
It's that quick.
yeah, it's not like a rock glacier or a slow-moving event. It's a very rapid fracture and then run out of that material down slope.
If you go back to your list of, bingo, right there. Would you care to suggest magnitudes of earthquakes that would generate those sizes?
I have not, but many folks have, and based on the amount of displacement measured at that trench site, these are likely on the magnitude of 7 or so. That's what, based on a trench dug right over here, where they can actually measure the displacement. This is very preliminary data that I'm showing you, but looking at, and so we've got much more seismic data. There's a chance we can measure displacement along the fault using the seismic stratigraphy. So in a similar way to measuring the displacement at the trench site, we can measure displacement using lake sediments. We've only just begun starting to do that, but I think it's possible. Yes?
You mentioned isostasy is one of the problems built this up with, but I think most cases in which I've heard of isostasy is on a much larger scale, like continental level. Is the idea that the ice sheet is kind of asymmetrically laying over this fault, and that one side has a larger change in mass during deglaciation?
Yeah, the concept, so this is a normal fault, and so that it's an extensional regime. And the concept is, I could bring up that map, but you have this huge mass of ice sitting on top of Yellowstone, and then also the ice on the Tetons. But it's particularly, from what I gather from these papers, it's really this mass of Yellowstone ice, because it's so much larger in mass than the ice on the Tetons, but of course that contributes. And then as we are unloading the crust, basically we are allowing essentially the fault to adjust to that unloading. Does that answer the question?
Absolutely.
Yes, ma'am.
What does deglacial mean?
Okay, so up here I just have a key or a little legend to this cartoon image of the core, and so I'm showing, there's a whole lot of terms here that I guess I didn't define. Yitja is this Scandinavian term for, it's sort of silly, I don't know why I put it on there, maybe it's because it's a short word and it fit in the box, but that's this organic, it's just organic rich, low density, non-minergenic sediments, so typical mud, lake mud, they squeeze between your toes if you walk out into a lake. Tephra right there. Tephra are volcanic glass deposits. So these are volcanic, so ash deposits that came out of some volcano to our west. In this case, from the Mount Mazama and Glacier Peak mountains. When those erupted, that ash was deposited right here in Jackson, and perhaps it's been preserved in soil sections, or perhaps not, but it is preserved in the lake. So it fell on the lake surface. Either the lake was frozen over and it subsequently melted down and was incorporated into the sediment, or it just fell on the lake during ice-free conditions and it settled down to the bottom. So that those layers are deposited there. And then I just have sand layers for these disturbance units, and then I wrote deglacial that is defining that basal unit there, which I should have kind of drawn a squiggly line at the bottom because we do not capture the bottom of the deglacial unit in that core or in the core on the bottom. But those are sediments deposited during the timing of deglaciation. So these are after the glacier retreated from the basin. These are sediments that were deposited while it was still occupying Cascade Canyon before it had melted out completely. Thanks.
One more last question if there is one.
Yes, sir.
Based on your comments about deloading of stress from the glacier melting, together with your list of seismic events, is there reason to believe that future seismic events will be more minor?
I don't have evidence to suggest that. Maybe I shouldn't have wrote major and minor. The minor there does not, I'm not referring to the size of the event. I'm referring to what is visually identified in the sediment sequence. And so these are either because they've only been identified in a single lake where I'm like, is this potentially a flood deposit? Or some sort of, erosion caused by a wildfire or something like that, until I can corroborate these ages, because in this case, they're not these big, some of the disturbance deposits are these really coarse deltaic sands, 10 centimeters thick that grade upwards to a clay cap in the middle of the lake in 240 feet of water. So it's virtually impossible to get that kind of deposit at multiple core sites in that water depth by a flood. That's probably not going to happen at Jenny Lake. Especially if I can date that same identify and date another deposit in a different lake and it has the same age. These minor disturbances are basically clay-rich minergenic units that are in Phelps Lake and Bradley Lake, and they could potentially have a different. There could have been a different event that caused those. So that's why I should have maybe just said sort of like preliminary evidence for disturbance. They're not minor events. I think they just might. I need to confirm them, but I wanted to put them up there because they're very real and I believe in them, and they line up with these paleo shoreline ages, which sort of confirms that perhaps they are indeed earthquake events.
Well, if you
So
want,
I can't say if the next earthquake is going to be minor or major.
wise man there. Now, if you did not get enough questions out, or if you can formulate some even tougher ones tonight, remember tomorrow at lunch.
Members lunch.
Members lunch. All it takes is a form and a check, and you can become a member. And if you got interested in earthquakes and what might happen, we keep talking